gases. Okay, so we jump into solid things to gases, fluid, liquid. Gas is a fluid, liquid is also a fluid. Chapter 8, gases. What we have here contains basic parameters of the respiratory system at rest. The basic parameter of pressure, volume, temperature. Probably you did these things in your chemistry as well. So number 2, pressure volume relationship of the air in the lungs. So, there is this ideal gas law, right? It's not something new. Probably you're doing in chemistry or you're done in chemistry. Am I right? Not yet? Have done. So, pressure volume relationship of so we are going to consider the air is ideal gas, although it is not quite correct, but we can approximate. Number 3, the gas laws. So we have for ideal gases, we have gas laws, empirical gas laws, meaning from experiment we find out they obey some laws. It's called the ideal gas laws. Number 4, mechanical model of the ideal gas. You will see how we can derive those gas laws by making a mechanical model of the gas and making some assumption. We can actually derive those gas laws. Number 5, energy contained in these gases, ideal gas. So we're going to have a lot of equations, okay, but we can use calculators, and there's no issue. We can train ourselves how to do these calculations. But let's study these concepts now. Why do we study gases in life sciences? Metabolism, right? So you must be knowing better than I do. What is metabolism? The food is burned. Am I right? Yeah. How? It's a chemical reaction. You need what to burn the food? Oxygen, which is a gas. So we should study gas laws, gases in life sciences. Cellular metabolism requires oxygen. It acquires the oxygen how? Respiration, right? Inhale, exhale. Two internal organ systems cooperate to provide rapid access to sufficient level of oxygen at the tissue level. What are those two internal organ systems? Lungs and blood, right? Blood system, organ system. Can you call it organ? Yeah, blood. What is the organ? Heart. Okay. The two organ is heart and lung. Lung is for gas, and the heart is for the blood. So these two, blood system and the lung system, they cooperate to provide access to oxygen, right? Oxygen is inhaled through the lung by the expansion and contraction of the lung, and then the bloodstream comes from the blood is pumped from the heart. It goes and collect this oxygen from the lung, right? You know the story better than I do, right? So there is the sacs in the lung and the blood comes in. So there is something going on. It will absorb the oxygen, the air, and we'll come to that. Okay, this is just a summary, right? I'm not going to teach all that, but this. So to show you the relevance in life science. Carbon dioxide, okay, another gas comes in. So you know the story too. So which we find as a component of exhaled air. In the exhaled air, you will have more carbon dioxide. How? It's a byproduct of this, the cellular metabolism, and is removed from the body in the reverse direction. First through the cardiovascular system and then through the respiratory system. Right, that's the bit of biology there. Now we come to the physics part. gas, the parameters that we have to be interested in, first, number one is the volume. You know what a volume is, right? Then again, we are going to link it to as a how it is relevant to doctors. Okay, there is an instrument called spirometer, right? It's a clinical instrument doctors use to measure the gas volume in the lungs. So here, it's a very useful instrument. I think it is still used in hospitals, right? Yeah, it's something, because the spirometer will produce some graphs. By looking at the graphs, the doctors can diagnose certain diseases. If the lung is functioning properly, it should, like the ECG, right? Like the heart is being studied for electrical signal, the lung is being studied for the inhalation exhalation process. If it is going smoothly, it will have a certain pattern. If it is not going smoothly, there will be, you can even, like ECG, you can deduce certain diseases. The person breathes into a spirometer mouthpiece, and their breath raises a jar that is floating between the two beakers fixed to the bottom plate of the instrument. So the jar is going to move up and down. This is the picture. So as the person exhale, his nose is blocked, so he's going to inhale through the mouth only. This jar is a floating jar. It will go up and down depending on the air that comes in and goes out from the human. This jar will go up and down. So there will be a graph which will be produced because this jar is connected to a certain pen or something that is going to draw on this paper. So there you will have a pattern like that. So that pattern, the height that goes up and down will correspond to the volume of the lung, air volume in the lung. So here, this part A, this is for a person breathing at rest. And this is when he is doing heavy exercise. There's a difference. While he is at rest, you will have that pattern from the spirometer. And when he is doing heavy exercise, you will have big changes in the volume. So the data identify various contributions to the human lung volumes. Number one, this okay, the inspiratory reserve volume. Number two, it's called the tidal volume, the regular breathing volume. So this when he's at rest. And number three, the expiratory reserve volume. These three volumes combined are called the person's vital capacity. Okay, so three volume, 1, 2, and 3. So this is called the vital capacity. The instrument that cannot measure, because there will be certain volume that will not participate while we are doing the inhaling and exhaling. There will be a volume left in the lung all the time. That is called the residual volume. And note that the volume scale is related to the volume after tidal expiration breathing. So the volume that we are measuring, it is after this tidal expiration breathing. The person inhales and exhales about 0.5 liters. So this corresponds to the tidal volume. What he inhales and exhales, it will be 0.5 liters. That is called the tidal volume. Right. These terms, probably I don't know whether you have studied this in your biology, these terms, and not yet. I don't know. Okay, but it doesn't matter. Okay, so I will give it to show you the relevance as a doctor. So you should know about this parameter volume. Now we go to the next parameter, pressure. Okay. What is the difference between force and pressure? Probably you learned this in your high school. That is, they are related, right? Pressure mean, it has something to do with the force. More force mean more pressure. But it's not exactly the same. It's like, I can give you a very nice example. Say you take a balloon, fill it with air, and you use your finger to prick it, to make a hole in the balloon. Can you do it? No. I mean, some maybe, but suppose you cut your nail also, okay, what matters is the pressure. Say, and let's say you apply a force on the balloon. This is the balloon. You use your finger. Finger has a big area, right? So the force you apply let's say you apply a force of small 10 Newton, okay? And that force will be distributed over this big area, finger area, let's uh, say 1 millimeter squared, or say 1 centimeter square. You apply 10 Newton, it doesn't pierce, it cannot make a hole. You take a pin. What is this area? Very small, right? Maybe fraction of, very millimeter, less than even millimeter, the thing. But you apply the same force, 10 Newton. There's no difference. You apply the same force with the finger also, you are applying 10 Newton. With the pin also, you are applying the 10 Newton. But with the pin, you will be able to prick it and make a hole. But with the finger, you will not be able to make a hole. The difference is the pressure. With the pin, you are applying a greater pressure because the force is not dispersed over a big area, it's a small area. But with your finger, it is spread over. So at any one given point, it is a small force. So that's the difference. So we define the pressure as the force applied perpendicular to a certain surface, the perpendicular component of the force, divided by the area. When the area is small, what happened with the pressure? The pressure will be greater. So now you understand the difference between pressure and the force. They are related, and this is the formula that relate the pressure to the force. Right, an example. Gas pressure P in a piston depends on the force, the perpendicular component of the force to that surface, exerted by the gas on the piston and the area A of the piston. Now you have a picture here, piston sees a gas in isolated conductor. The piston is mobile, can be moved along the x-axis. The piston is assumed to move without friction. What's the question? Okay, it's just to explain the pressure. Okay, so the pressure going to be the force divided by the area of the piston. What about the unit for pressure? Force is in Newton, SI unit is Newton, and the area in Newton will be meter squared. So the unit for pressure is Newton per meter squared. But as always, we have, I'm just worried, did I start the recording? Did I or did I not? Please tell me. Yeah, I started. Where is my slide? Right. So we don't say Newton, I mean, we can say Newton per meter square, but we have one word for it, which is Pascal. So what is the SI unit for pressure? Pascal. Pascal means Newton per meter squared. But Pascal is not P. It is two letters, one big P A. You have to write like this for Pascal. If you write P for Pascal, that is wrong. Pascal is P and a small a. There are other units of pressure, yes. Millimeter mercury, centimeter mercury, and so on. Okay, so 1 millimeter mercury, which corresponds to this much of Pascal. The atmospheric pressure, okay, the pressure that we get from the air molecule hitting all around us, okay, is the atmospheric pressure, because each molecule, when it hits our body, it is applying a force. So the combined force divided by the surface area, it's called the atmospheric pressure. So one atmospheric pressure, the atmospheric pressure can vary. The standard atmospheric pressure is this many kilopascal, 101.3 kilopascal. Or in other words, 1.013 10 to the power 5 Pascal. And in terms of the centimeter mercury, it is, or millimeter mercury, it is 760 millimeter mercury. Do you need to memorize this? No. But you should have an idea, okay, because you probably have you seen the barometer which measures the pressure. So you should have an idea what atmospheric pressure in the mercury column that it can lift 76 centimeter. It can lift. So that's why it is 700. Yeah. Huh? Toe is another unit. Yeah, I forgot. Torr is another unit. I cannot tell you because I forgot. Torr is another unit for pressure. So maybe you are right. Is equal to 76 centimeter mercury, maybe. Yeah. But I cannot say with confidence because I forgot. Okay, maybe it is there or not. Anyway, never mind. Okay, if you need, we have to give you. Nobody is supposed to memorize that. But I told you, as I told you, you should have a rough idea. One atmospheric pressure is about 76. Standard, not about exactly. The standard atmospheric pressure is 76 centimeter mercury or 760 millimeter mercury. According to him, it is. No, I don't think. Maybe 1 millimeter mercury is Torr. Never mind. It's okay. I forgot. I completely forgot. So the third parameter is, in that case, you will say what atmospheric pressure is 1 toe. I don't think so. No, I don't think so. Maybe that is the pressure unit you are measuring the tire pressure. Tire pressure, how much pressure you put it into your tire? 35. Is it centimeter mercury? No, I don't think so. Maybe it's 1 toe or something like that. Anyway, let me forget about it because I'm telling all wrong things. So I don't know why you brought it up. Okay, I forgot what toe is. Right, temperature. That is the third parameter. Shall we stop? Okay, shall we stop? Okay, because it will go. Right. Any questions? No? Right. Yeah. Yeah. Area of the pin. The surface that is in contact with the balloon area, because the surfaces are the balloon. So area of the force is spread over the pin area, not the whole balloon, right? It's area of the pin. The force is without fail. So we have started this chapter 8. We were able to cover a few slides. So I will go through that again quickly. Gases. The chapter is about gases. So we are moving from solid, rigid objects to gases. They are fluid. There are no more solids. So we said the basic parameters of respiratory system at rest. We looked at like volume. We started with volume. And then we also mentioned the clinical instrument, which is called the spirometer. It measures the volume of air in your lungs. So that's why, it is the relevance to medicine that we should study gases. So volume, you understand, this is the picture of a patient being asked to breathe in and out of the spirometer. So by looking at this pattern, if there is any irregularity in the pattern, that can diagnose sickness. Then the next one is pressure. So we define the pressure. This is the formula. So I gave examples of difference between pressure and a force. I hope you remember them. And the units for pressure, SI unit is Newton per meter squared, force divided by area measured in meter squared. So we have the name, single name for that. We don't keep saying Newton per meter squared, we say Pascal. And it is not just one letter, it comes with two letters, the capital P and A. So that will be the symbol for Pascal. There are other units, of course. The mercury, in terms of how much mercury the air pressure can push up, that is, it's millimeter mercury and also centimeter mercury. So 1 centimeter mercury is 10 millimeter mercury. It's understood. That's the conversion between millimeter and centimeter. And 1 millimeter mercury is this much of Pascal. The pressure of air, the atmospheric pressure, it's also a fluid, right? So it exerts pressure, and it is in kilopascal. It will be 101.3 kilopascal. So if you are expressing in Pascal, it will be 1.01 10 to the power 5 Pascal. In terms of millimeter mercury, it is 760 millimeter mercury. Do you have to memorize it? No, I don't think so. Right, then the temperature. So this is where we stop, right? Temperature. That is the third parameter that we pressure, volume, and then temperature. There is laws in thermodynamics. The zeroth law of thermodynamics says if something is in thermal equilibrium, every part of a system is in thermal equilibrium. Every part of the system has the same temperature. That's the definition of thermal equilibrium. So you know what is thermal equilibrium. So you have a system. If you say that system is in thermal equilibrium, what it means is everywhere in the system, it is the same temperature. More specifically, to make it very exact, we can say like this. Suppose we have two objects in a system, A and B. If A is in equilibrium with the third object, say something close to it, say maybe object C, and object B is in equilibrium with another object, say object D, that means if object A and B are in an equilibrium with the third object, like the thermometer that you put in, that means A and B are in thermal equilibrium. So this is another way of putting, in a system, thermal equilibrium means everything in that system has the same temperature. So pressure volume relationship of air in the lung. So this is what you're going to, the relevance to biology. So here, you know what this is, right? Lung. Okay. So I have to introduce. Number one is the lungs, right? The interior of the lung. This is number two, which is pleura. I don't know how to pronounce exactly. That is this layer, membrane. That is called the pleura. The double-layered membrane that encloses the lungs. So we have such a layer. So that is what defines the lung. Okay, but it's a double layer. So between the layers, we have a gap. And number 3, this is the cross-sectional view, right? That's the rib cage skeleton, the rib cage. These are the rib cage. 5. So this is what comes from your mouth and the nose, the trachea. And it branches here. These are called primary bronchi. Trachea branches into bronchi. Primary bronchi. Then here we have the diaphragm and also the muscles, the actions of the muscles, so like that. The muscles, no, abdominal muscle, bronchi and the abdominal muscle. And then intercostal muscle, they are not shown directly, but it's shown by the action from those intercostal muscle. The muscle that can help it to expand and shrink, right? The diaphragm as well. And then these large arrows indicate the effect of the external air pressure on the chest. So you know the lung shrinks, expands, thereby inhaling, exhaling. Right. Now what is important for us, other than this biology thing, the pressure in the lung. You call the pressure in the lung as P subscript lungs. That is the pressure, the absolute value of the pressure in the lung. We put it like that, P lungs. And we talk about the pressure in the membrane, okay, the double layer membrane, in the gap here. So that is called the pressure in the gap. So I hope you are following me. So we talk about two pressure in the lung and the covering, the membrane. So inside the membrane, we call it the gap. So the pressure in the gap. So these are the absolute value of the pressure. Now, then we say pressure in the pleura. Let me start with this. Pressure in the alveoli. What is alveoli? Also lung, right? Alveoli is another word for maybe the technical word for the lungs, right? So why we have two things, pressure of the lungs and pressure of the alveoli. This is the absolute pressure. Here the pressure of the alveoli is, we put the 0 atmospheric pressure. So subtract the atmospheric pressure. So maybe this pressure may be in terms of say millimeter mercury, maybe it is 765. That is the pressure in the lung. You subtract 760, what do you get? 5. So this is called the gauge pressure. So now you know the difference between the absolute pressure and the gauge pressure. Gauge pressure is you put the 0 at the atmospheric pressure. So how much more or how much less than the atmospheric pressure is called the gauge pressure. How do you get it? Just subtract the atmospheric pressure, you'll get the gauge pressure. So please understand the word gauge pressure, okay? It is important. For example, the blood pressure that we measure, say you say the normal pressure is 120, right? It is in, I think it is in millimeter mercury, right? Yeah. But it is gauge pressure, not absolute pressure. Because the blood pressure has to be greater than the atmospheric pressure. Otherwise, we will be squashed in. So when you say it is 120, it is 760 plus 120 is the actual pressure of the blood. Okay, good. So similarly, for the gap, the pressure inside this is the absolute value, but you say pleura, the name of the gap is pleura, right? So like lung is alveoli, gap is, the technical name is pleura. So pressure inside the gauge value of the pressure in the gap called the pressure of the pleura. Okay, so now we hope you understand the difference between P lungs and P alveoli and P gap and P pleura. Okay, One is absolute pressure, the one is gauge pressure.
Is the other one named absolute pressure?
Absolute pressure. I mean, as it is, without subtracting the
Absolute pressure is this pressure without dividing.
real pressure, not divide, without, yeah. The real pressure, absolute pressure, okay? Atmosphere and the gauge, plus the gauge pressure, okay? So, why do you, because it's very convenient to talk in gauge pressure, we will see in a minute. Right. There is a graph here. This is the green line is the graph of gauge pressure of the lungs, okay? Not the absolute pressure, but the gauge pressure. And this is the pressure volume relationship of the air in the lung. So the green, what we have is the volume, and here we have the pressure in kilopascal. So while we, inhale, exhale, the volume is going to change, and corresponding the pressure will also change. So this line, the green line, is the pressure in the lungs, but as a gauge pressure. And the blue line is the pressure in the gap at the same time. Okay, so as the volume changes, the pressure changes. Now, if you look at this graph, what is this graph? The difference between difference between the lung pressure and the pleural pressure. Okay, the gap pressure. It should be always greater than 0, right? Otherwise, it is going to collapse. Okay, so you see that this value, the red line, is the difference between the lung pressure and the gap pressure. It has to be greater than 0. Yeah.
Does the volume and the flow actually equal same as the lung?
No. Yeah, it is not. So the volume, probably the volume of the lung volume. Okay, so it doesn't correspond to that. Yeah, it's a bit confusing, right? Yeah. So you can say it's a small gap. So you can say the volume here is the volume of the lung, the total lung. Okay. So because it cannot be. So the volume is the volume of the lungs, and the pressure is only the pressure which is different. Okay. Thank you to pointing it out. I didn't think of that. Okay. Right. Good. Now this is a table because to give you the relevance to life sciences or in medicine. Why should we study pressure? It is not only the lung pressure. We doctors talk about pressures other places as well, right? You know that. Glaucoma, for example, what is it talking about? The pressure in the eye. So here, blood pressure. Then we have this systolic and diastolic. Of course, you know better than me what they mean. So as I told you before, is actually gauge pressure, right? What is mentioned is gauge pressure. So here in millimeter mercury, that's right. So how much above the atmospheric pressure? It's a gauge pressure. And there is this large veins. These are in the in the heart itself, right? Or the big artery or whatever. Okay. So in the vein, it can be as small as 4 to 15. Eye, that is where eye pressure goes up. Then you have what you call glaucoma. Yeah. And that's not blood, right? It is some other fluid maybe that is keeping the pressure. Brain and spinal fluid. Okay, that can we talk about pressure. Doctors, bladder pressure. While it is full, these things can indicate diseases if they are not in the range. Chest cavity, I don't know what it needed. Anyway, it's just telling there. Inside the lungs, okay, that's what you just talked about. Digestive tract, esophagus, stomach, they measure these pressures as well. I don't know how it is applied. There must be. Intestine, middle ear, that's important, right? Sometimes when you go in the plane, when the planes take off, because the pressure changes. The cabin pressure is not necessarily atmospheric pressure. It can change, and then you get the pain in the ear. Right. So I hope I convinced that you should study physics. Okay. Right. Let's go. Boyle's law. This you did in the chemistry, so I can probably go faster. Gases obey some law. Actually, ideal gas, but even air, in a certain condition, we can say it is almost like the ideal gas. If you take a fixed volume of a fixed amount of air, not volume, fixed amount of air, say in a container like that, let's say we have something like 3 moles of air. You know how we give the amount of air, not in mass. You can give in kilogram, gram also, but it's easier to talk about moles, right? So 3 moles, a certain amount of air. It at a certain temperature, it will have a certain volume and a certain pressure. So it will have P1, V1, T1. Suppose I change one of them, for example, I keep this fixed and change the pressure, the volume should change, right? It changed. But doing experiment, they found out, keep the temperature constant. If I change the pressure, increase the pressure, for example, volume decreases. Then we took some data and find out it actually obey inverse relationship. Say this is pressure of the volume, this is pressure, you get a curve like this. So if you take, say, this P1, V1 and take another P2, V2, it is P1, V1, the product remain constant. That means P is inversely proportional to volume, mean proportional to 1 over volume. So that is called the Boyle's law. So it can be written like this: P1 V1 is equal to P2 V2. The product PV is a constant. So initial, final, or 1, and 2, whatever symbols you use. The product of pressure and volume of a gas at constant, you have to stress this, okay? You have to keep, because there are 3 parameters we have to worry about: pressure, volume, temperature. So we have to study 2 at a time. So we keep the temperature constant, then we see pressure and volume has an inverse relationship. So now we can do a question, okay? This question is, we have a ocean, water, right? And there's a bubble here, and the bubble forms. You know what is a bubble? It's an air bubble, right? Bubble means it's an air bubble. So that is just something that is only air. And the bubble goes up. Okay, density of the air is less than the density of water, so it will go up. As it goes up, let's say it's formed, there may be a fish there, it was breathing and it is giving out the air, so a bubble formed and the bubble goes up because the density of air is less. As it goes up, we will observe something. It increases its volume. Why? Pressure decreases, right? The equation for the pressure as a function of the height is this. We're not going to prove it. H is the depth at the, and H is equal to 0, the pressure from the fluid only, because there's no fluid above that, right? So only air pressure is there. So the pressure there from the fluid is 0. As you go down to the ocean, the pressure increases because you are pressed down by volume of the column of water above you. So the pressure will be higher. The equation is given by this. You don't need to prove it, I'll just give the equation. H is the depth below the surface. Rho is the density of that fluid. If it's ocean water, density of the ocean water. G is 9.8, okay, the gravitational acceleration. How it comes there, we can prove it, but don't worry. So that is the equation for how to get the pressure due to the ocean water. It is a function of the depth only, right? So that means the pressure at this point will be atmospheric pressure that is coming from the volume of the air plus the pressure coming from the ocean. So the pressure of the bubble here will be this atmospheric pressure plus depth of the ocean, how much deep it is, multiplied by density of the water. Ocean water will be slightly different from the river. It doesn't matter, we just put water multiplied by G. So as the bubble comes up, what is the volume, the pressure here? The pressure here will be only atmospheric pressure. P1 will be atmospheric pressure plus H rho G. Right. So because as it comes up, the pressure is decreasing, according to Boyle's law, we are going to assume something. Temperature is constant. Is that true, strictly speaking? No. Strictly speaking, not true, but we want to make it easy for us. We'll assume the water temperature is same all the way. So assuming, is that there somewhere? No exchange of heat. That doesn't mean temperature is constant, right? Yeah, yeah. Okay, the bubble has a certain temperature here. As it goes up, no exchange. Maybe the temperature is greater, but no exchange of heat between the bubble and outside. That means the temperature of the air inside the bubble will be the same. So this guarantees us the temperature of the air bubble is the same. Ocean temperature may be different, who cares? There is no heat exchange. Right. So where are we? Now, I mean, this is we are jumping to the other law. So, but here, don't worry about it. Now we know Boyle's law is obeyed, right? Because the temperature is constant. Therefore, P1 V1 is equal to P2 V2. So we'll apply it. So the question is, find what fraction. That means he is asking us to find this change in the volume divided by initial volume. That's what he's asking us to find. When you say fraction of the, what fraction would the volume of the bubble increase by the time? So he's asking change in the volume divided by original volume, that is a fraction of the volume that is changed. Okay, so let me do this first. Delta V V1 means the change in the volume, right? V2 minus V1 divided by V1. So this is what we need to find. V2 divided by V1 minus 1. That is some algebra here.
How did it come V2 minus V1?
You want the step from here to here? From here to here? Yeah, okay.
So V2.
Yeah, this is 1. Okay. All right. Okay. Yeah, I know it's algebra, but maybe you didn't think about it. So, right. Anyway, so I need to find this, right? So I'm coming back to the Boyle's law. From the Boyle's law, I can see if I do some algebra again, V2 divided by V1, I take this to this side, take to that side, then you get this. Don't make mistake, right? Because inverse relationship, it is, the product is the same, so that you mean P2 V2 is equal to P1 V1. So V2 over V1 will be equal to P1 over P2. So P1 is what? Yeah. V2 is this. Then you substitute the what is given. P atmosphere in Pascal is this. And H is given, where is it? 1000 meter deep. So H multiplied by density of water, 1000 kilogram per meter cube. In gram per centimeter cube, it is 1. Okay, but in that is not SI unit. SI unit is kilogram per meter cube. What is 1000? That is 1000 multiplied by 9.8. And here again you put the atmospheric pressure, you get this value. It's a ratio, right? So it has no same unit. So it has no units. Then you substitute for that here, and that's one, you get this. Done. Because I already solved it in the slide, I don't have to write anything, just I followed it through. Okay. Shall we go to the next slide? Any questions? Yeah.
From the question, how do I know the fraction of volume of
Yeah. This is the question. By what fraction would the volume of the bubble increase? So, final volume minus initial volume. Increase. Okay. If you say decrease, then V1 minus V2. Right. Now, this is what? To show you further about the Boyle's law, say suppose you do the experiment with one temperature T1, you'll get this graph. Suppose you go to another temperature T2, which is greater than T1, you will get this one. So you can see as your temperature increases, the graph also shift to higher and higher. We have a question now. Which of the four graphs on the following slide is consistent with Boyle's 1664 experiment that led to Boyle's law? Okay, he could have, Boyle is a person, he done this experiment, he plotted a graph of pressure versus volume. So, the graph should look like this, right? If you don't get a graph like that, so, then, you have to choose from the graphs available. Yeah, both look, this is also possible, this is also possible, right? This is wrong, and this is wrong. Which one of these two? You need to know the history, how Boyle did the experiment. Did he start with the small volume and increase the volume, or did he start with the big volume and decrease the volume? I mean, you could do the experiment either way. We don't know unless you know the history, how he did it. And I believe he started, I keep forgetting this. No, I mean, did he start with the big volume and reduce the volume by applying pressure, or did he start with the small volume? And I think it is the other way around. He probably started with the big volume. Practically, it's easier to do that way. Start with the volume, apply the pressure, and then measure the decrease the volume and measure the pressure. So if I am right, that means this is the correct one, right? Because we went this way, not this way. But again, I'm not sure because I forgot. Maybe you can read the textbook and find out. Okay, I'm sorry about that. It's just a historical fact. Okay, not nothing else. Charles' law. What is Charles' law? The PVT, there are three parameters. In the Boyle's law, you look at how they behave, the two parameters at a time. So this time you fix the pressure and see how the volume changes when you change the temperature. Charles did it, and he found linear relationship. So that means the fraction is constant. When it is inverse relationship, the product is constant. Linear relationship means that when you double the temperature, volume doubles. When you triple the temperature, volume tripled. That is linear relationship. Then you learn this in the proportionality in chapter 1, remember? Then the ratio is constant. Either you can say V over T is constant or T over V, another 1 over that same constant. Anyway, it doesn't matter how you put it, okay? So the ratio is constant. So more useful to put it this way, because you know V1 over T1 is equal to V2 over T2, or initial, final, final. When you do question, you know, sometimes it's preferable to put it that way rather than. There is one important thing. This is, you know, you can write it like this only when you give the temperature in Kelvin, not otherwise. So this equation assumes when temperature is 0, volume is 0. That happens only when you give the temperature in Kelvin, not otherwise. Okay, this is very important to remember. The temperature must be in Kelvin. Charles' law applies only to experiment done at constant pressure. Okay, such experiments are called isobaric experiment. Okay, this name, bar mean in Latin pressure, iso mean same, so same pressure. So we call it isobaric experiments. So we keep the pressure constant, then we get the Charles law. What about the previous one? What are you going to call the Boyle's law? Is done in iso what? Isothermal. Thermal mean temperature. So you know these words, okay? Isothermal is Boyle's law. Isobaric experiment do, then you get the Charles law. Right. Charles law, we come to this absolute temperature. See, we take gas at a certain pressure because we fix the pressure, right? Isobaric experiment. Say P1, and you collect some points. Then as you change the temperature, what do you expect? It will keep decreasing. At one point, we cannot do that experimentally, but we can kind of extrapolate. So we can come, you know, minus 10 degree, minus 20 degrees, minus, but you know, there is a limit to, we cannot have a minus, you know, very difficult to come to, but we can extrapolate the graph with whatever we took. Say we took experiment only up to here. We can come only up to say minus 77. Then we can draw this line, and if we extrapolate, we can kind of say, okay, if we are able to do the experiment at this point, which is this temperature, it will come to 0 volume, which is not possible. We can only approach that temperature. Then, you know, you do another sample, which is at a different pressure, and you do the experiment. And when you extrapolate, it comes to the same place. So now we are convinced. So we can define the another temperature scale. We will say Kelvin scale when the volume comes to 0. That is the absolute 0. So this is the equation. Temperature in Kelvin will be temperature in Celsius plus 273.15. So we need to know this equation as well, because sometime in a question they will give the temperature in Celsius. So you should convert it into, especially to apply to the Charles law, where there is a temperature, you need to convert the temperature to Kelvin. Okay, now we combine both these laws, which is the PV. P is proportional to 1 over V, and P is proportional to, actually the volume is proportional to, right? Okay, let me put it this way then. V is proportional to 1 over P, and also V is proportional to 1 over T. If I combine these two, I can say V is proportional to 1 over Pt. I mean, V is proportional to 1 over P. This is incorrect, right? Yeah. Okay, I'm sorry. So V is directly proportional to T. So if you combine these two, you will say V is proportional to T over P. So that gives to, we can say, looking at this, PV over T is a constant, right? PV over T is a constant. Then people went on to do very rigorous with data and all. They found out this constant is N is the number of amount of substance you have multiplied by the constant R. This constant R is called gas constant. It's not something new, right? Is it called gas constant? Yeah. It's not here. It's called gas constant, right? Yeah. Huh? Yeah. Well, I mean, we do it with real gases, okay, but we figure out it is not exactly right. But for ideal gas mean very much diluted gas and the pressure is low, then it become like an ideal gas. Approximately is correct for real gas. Okay. Yeah. In the exam. Yeah, we will ask. Yeah, we have to assume ideal gas. Okay. Otherwise, we cannot apply this equation. Probably the question will mention, or it will say an ideal gas, and so on. But in the real example, the bubble, air bubble, we apply the Boyle's law, right? We just, assume it's an ideal gas. That's it. Yeah. Okay. So that is called the ideal gas law. And the value of R in SI unit is this, 8.314 joules per Kelvin per mole. Mole, okay? Mole. You know what is mole? What is mole? Is Avogadro number, yeah. It's a number actually. It's like when you say 1 dozen, 12. So 1 mole is big number. It's just a number, okay? It's a name for collection of numbers, a large number, that's all. Avogadro number? No. 8.314? No. It will also be given, okay? It will be given. Right. So then we have the law, which is ideal gas law, PV is equal to nRT. Only this is constant, right? Strictly speaking, R, we can choose different number of moles. So the only constant, universal constant is R. So that means I can write it like this, PV divided by NT is a constant. The most general way of writing the ideal gas law in this manner. So you can say PV divided by NT is a constant. Usually, N is a constant in most of the question, but in some question where there's a gas leak or something, then N is not a constant. Right, gas in a constant volume gas thermometer, we have a question now. A gas in a constant volume, so it is saying, here we have a question where the volume is constant. A gas thermometer registers a pressure of 95 kilopascal at 100 degrees. Assume ideal behavior. See, so we can assume it as an ideal gas. What is the temperature of this gas when the pressure is this? So what we have here, this is P1 initially. This is T1. I deliberately didn't put the capital T, so to reminder for me, because it is not in Kelvin. So otherwise I will use the capital T, just so I don't forget that, okay? So I put small t. And this is P2. So volume is constant. So we write this, P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. V constant cancels. Number of moles constant. Okay, we nothing is leaking out or anything. So it's become this. Right, now it's a matter of substitution. We have everything we need. So you take your calculator. Ah, yeah, I already in my, let me show you. Oops. That R is gone from the beginning. See, this is how did I get this? PV over NT is equal to R, right? R is a constant. That means P1 V1 divided by N1 T1 is equal to P2 V2 divided by N2 T2. The R is the constant, it's a universal constant. Therefore, from this I get this. There is no R here. Okay. Then for this particular question, volume is the same, number of moles is the same, so you reduce to that. Now I can take my calculator. How do I get my calculator? Okay, right. I have to escape from this. Okay, all right. Calculator. All right. So what do I do? P1, tell me. It's in kilopascal, right? Both P1 and P2 are both in kilopascal. Do I need to bring it to Pascal? No need, because the ratio either side, okay, so we can put it in kilopascal. So I'll bring in my fraction. So P1 is how much? 95. And divide by T1. Here we have to be careful. What we have is the small T1, so which is 100 Celsius. So we have to add how much? 100 plus 273.15. Yes, yeah, better have it. And bring it up. Equal sign, alpha equal. Again put the fraction. P2, 250. Commander, what do you do now? X. Shift X. You will get the answer in Kelvin, right? Yeah, because. Yeah, or you can do that. Yeah, maybe a good idea. So it saved time. But I really didn't want to do it because I don't want to confuse anyone. Shall we go step by step rather? Okay. So let's get the value. Then I will do it again with the. So are you all with me? So what we will get is the value of shift calc. That's not the answer. 981.9. So you get the answer to be 989. 0.9. Okay. So this is in Kelvin. Kelvin. Okay. This is in Kelvin. So you have to subtract 273.15 to get the answer. So maybe because in an exam you want to save time, right? So like you suggested, what you can do is, hope you're following me, you can go down and you can put what? You will say X, yeah, X. X is we assume X is already in centigrade. So you have to that we have to add 273.15. Now you solve it. The answer will be directly in Celsius. So it will save you time, right? 708.8. So that is the answer. Right. So we can continue now. The following slide shows 5 processes by which a given amount of an ideal gas is brought from initial to a final state. Which process occurs at constant temperature? So if the temperature is constant, pressure and volume is going to change, right? So the graph should be, the relationship is inverse, right? It should be a curve like that. So it's all of them are pressure volume graph because temperature is constant. The answer is, yeah, it is C. Why not E? It's not the shape of the curve, right? The shape of the curve is inverse, it's like that. It's not concave. Right. So now we come to kinetic gas theory. So this originally, this ideal gas law was found empirically, meaning just by doing experiment, collecting data, then you find. But later people was able to theoretically prove it using these postulates of kinetic gas theory. We say in the air, the volume of the air particle is negligible. It's like almost zero volume. So air molecules are very small, right? A molecule, you're talking about each molecule. Say if you take oxygen molecule, one oxygen molecule, it has a very tiny volume. So we can ignore the volume of individual particle. So this is postulate number one. Then we say the gas consists of very large number of identical particles. So it's only oxygen identical. They all in air it is not identical. One is oxygen, one is but we can assume because they're so small. That's why we have to make all these assumptions to theoretically obtain the ideal gas law. It is possible. So the second postulate is large number of identical particles. Number three, the particles are in random motion, meaning one molecule will go this way, other one will go that way, this way. There's no preferred direction. Strictly speaking, it's not true. Even air molecule has weight, mass. So the preferred direction will be down because the gravitational force is pulling. But we are saying it is small particle, they have very little tiny weight. So this postulate is okay, right? So random, the directions are all random. 4, the only form of interaction between the particles or between particles and the container walls is elastic collision. Remember collision, elastic means no kinetic energy is lost. They have kinetic energy only, no potential energy because we ignore the gravitational force. So the kinetic energy, when they make a collision between molecule to molecule or particle to particle or with the wall, nothing is lost. So we take these 4 postulates and we can prove the ideal gas law. You don't have to do, but it's very interesting. Okay, you can look at it and see the derivation and all. It is in the book, but we will not do it now. It's very interesting, really, because what is proved experimentally with these postulates, we can arrive at an equation that proves the ideal gas law. We get this. With this postulate, we do a few things, you will get this. You see that PV is equal to, not yet ideal gas law, but I'll come to that. What is N? Is the number of particles that we are considering. M is the mass of just that one identical one of the particle. And this is the average speed, because they will have different speed, right? One molecule will be going 10 meter per second, other one will be going 2 meter per second, but average speed. So that's with this mean average. Square of the average of the squared speed. Right. Now, this is number of particles, this is mass of one particle. So what is this? Total mass. This is the number of particles, this is mass of one particle. So the product will be the total mass. We can write the total mass this way also, where small n is number of moles and big M is molecular mass. So that also will give you the total mass. So that is why we can replace this by this. So this is the total number multiplied by mass of one particle. This is the number of moles multiplied by the mass of one mole, right? That is molar mass, molecular mass, molar mass. So they are both equal. Okay, so we come to that. Now let me go to the next slide. Now we are doing something here. See, I took it out of that equation, previous equation. Look at this. What is this? What does it look like? Kinetic energy. Yeah. Kinetic energy of one particle. Mass of the particle, the one particle multiplied by speed squared. So this is kinetic energy. Right. What did I do now? I do something now, which is, yeah, I multiply by 3, divide by 3. Okay. You can do that, right? You can take anything. What is 3 divided by 3? 1. So I can multiply by 1 anything. It doesn't change. Still it is the energy of the particle. Now, forgive me, right? What did I do here? I want to get the expression for the energy. Okay, it is not the previous expression. This is, we have it, PV is equal to this. That's fine. Okay, leave it alone. Now I am going to find the energy of a air particle, a collection of air particle. Energy is kinetic energy multiplied by number of particle will give you the total energy, total kinetic energy. We don't have any potential energy because we are assuming they are tiny particle, they don't have weight. Yes.
U is the
total energy. U usually, maybe in chemistry, U stand for the total energy of collection of particle. So kinetic energy of one particle multiplied by the number of such particle will give you the total energy. It's only kinetic energy, nothing else. That's total energy. Now I'm going to do this. Multiply by 3, divide by 3. Right, and then I will arrange things. So 1, 3 go this side and this stays this side. Now look at this. This is what we proved in the previous slide. This is equal to PV, right? So you going to, instead of replace this with PV, and then put the ideal gas law. PV is equal to nRT. So you now proving the internal energy of an ideal gas is equal to 3/2 nRT. Okay, that is our final purpose. Yeah.
Can I remove 3/2?
No, no, you cannot. Yeah. I mean, we are using, we come this far, right? With the kinetic energy theory, we come this far. We have come this far by using our kinetic energy theory. We know this is equal to PV. We have come that far. So now we have proved U is equal to 3/2 PV. Then we use the ideal gas law to replace the PV by nRT. Okay, it's not that we are proving the ideal gas law. We use the kinetic energy theory to show that the internal energy of the gas is equal to 3/2 nRT. The energy depends only on the temperature. It's not a function of the pressure or the volume. The internal energy of ideal gas, okay? Monoatomic ideal gas. If it's a diatomic gas, then it will be different. When you say particle, it's just pure one atom only. Okay, so that's the internal energy of an ideal gas of a point-like particle Okay, point, just a point. Okay, so it doesn't, it's not the same. If for oxygen it's a diatomic, right? So it is not point like, this expression will change. So we don't go there, we just stop with the okay, that is independent of the pressure and the volume of the gas. Done. Right. I know I have promised you I will solve question, but it's okay. Next class I will solve both chapter 6 and 7 question. Okay, but today we have time today. I didn't take the attendance. Yeah, you have a question?
Can you open the formula sheet?
Yeah.
The upcoming fractions are different from what.
I will open it now. Okay, give me a second. This one? 3.
See, the last thing we have that is the kinetic energy of a gas.
Where I don't see it. 8, chapter 8. Yeah.
Yeah.
Okay.
At the bottom, the fractions
This one.
are different. So does that
Is it different?
not the total energy? I'm talking about the first.
This one
Yes.
is different.
Yeah. So
Really? That must be a mistake then. 1/3, maybe.
yeah, it's here. It says 1/2.
1/3. 1/3. Come on, you scared me. Yeah, we do the same proof. Just come here. Say, yeah. Nothing. It's the same thing. It's just a proof. I shouldn't have it here, but I felt, why don't you show the proof? Okay. This is the same thing. Then you're proving and come to this. Okay. I shouldn't put the proof in a formula sheet, but I don't know why I did that.